I am Mr. True. In this video, we're going to do a lot of examples, just a quick introduction to a theorem, where we look at the relationship of two triangles together, or inequalities in two triangles as opposed to just inequalities in one, like we did in the last video. We want to compare two triangles and determine if any conclusions can be made about the relationship of sides and angles. The hinge theorem, kind of going back to this SAS type idea, or the SAS inequality theorem, if two sides of one triangle are congruent to two sides of another triangle, so it kind of almost sounds like we're talking about congruent triangles. You know, the side-side-side theorem, the side-angle-side theorem, the angle-side-angle, and the angle-angle-side, where you had pairs of congruent parts. Now, we're not going to be using, this isn't side-angle-side congruency theorem, it's a side-angle-side inequality and I ran out of room theorem. So again, we have those two pair of congruent sides, and the included angle. Notice the angle symbol is in between the two sides. When you have two sides come together and make an angle, that angle is said to be included. It's kind of like in between the two sides that help to make it. So, and the included angles are not congruent. That's why we're not talking about side-angle-side congruency theorem, because the angles are not congruent. Then the longer third side is opposite the larger included angle. What that means, or what that looks like, as opposed to just a bunch of words, but an actual picture, is if the measure of angle A is greater than the measure of angle X, then the length of BC is greater than the length of YZ. Now, what I did not include in my conditional part of my if-then statement is that, I have these pairs of congruent sides, that BA is congruent to XY, that AC is congruent to XZ. Well, if angle A is larger than angle X, and we do have this side-angle-side pattern, then the side that is opposite the larger of the included angles is going to be larger. So BC is greater than the length of YZ. Couple of examples, and again, I've got these two plus another three coming up, so there's lots of examples. I've got a couple of triangles here. They are sharing a side, so AC, if we were doing a proof, we would say that AC is congruent to AC with the reflexive property. So I've got two triangles. They both have a pair of congruent sides, another pair of congruent sides, and we're looking at the included angles in between those sides, but they're not equal. So these triangles are not congruent, and now what we know with this theorem is that since angle BCA is only 35 degrees and angle ACD is 41, well, side angle side, but 41 is larger, so that means that AD is going to be greater than BA. Okay, well and that's this hinge theorem, if you will, just in practice. Over here, the same thing. Now this one, these kind of look like they might be the same measurement, but 35 degrees is close to 41, so could be just drawing error. This one's on purpose. I got this one here. I've drawn these two triangles. Again, we have a shared side, so YW is congruent to YW because of the reflexive property, so we are looking at that side angle side pattern. I purposely made this segment kind of basically look like I tried to make it look like a perpendicular bisector. I mean, that's not really what 100 or 80 degrees looks like. You should notice with a lot of your geometry problems, especially if you take some of those standardized tests like the ACT or SATs, they always say, figure not drawn to scale. You can't say something is 90 degrees because it looks like it, or two parts are congruent because it looks like it. You have to go by the information given to you in the diagram. And while these two angles purposely look like they're equal, you are told that this one is 100 and this one is 80. So that was on purpose. Don't ever trust your diagram. Trust the information given to you in the diagram. 100 is greater than 80. That means that XW is greater than WZ because it's opposite the greater angle. So that's the end of my first two examples. I got three more coming right around the bend. Three examples and we're done. So we have triangle ABC and triangle X, Y, and Z, and can we draw any conclusions about the length of BC compared to the length of YZ? Now, why would I pick out that? Because we need to be working with those included angles. We need If we have two pair of congruent sides, then start comparing the size of the included angle. While the 35 is included in these two sides that are marked congruent to these two sides over here, 42 is not. So our answer to this is we can't draw any conclusions because we're not fitting the pattern that 42 is not included. Okay, over here we have a couple of adjacent triangles, and I need to add that congruency mark in there. So we have we've got two triangles. We've got there we go. Now it's good. We have a pair of congruent sides. We have another pair of congruent sides. We have a comparison of the two included angles. And let's see, we had 15 is greater than 10. So the fact that 15 is greater than 10 means that 60 degrees needs to maintain a relationship where it is larger than 5x minus 20. So 5x minus 20 is less than 60. We're going to add 20 to both sides and get 5x is less than 80. We're trying to solve for x, of course. We're trying to find an x value that's going to keep this expression less than 60 because 10 is less than 15. We're going to divide both sides by 5 and get x must be less than, let's see here, there's 1, 5, and 8. If you take a 5 out of 8, you get a remainder of 3, so 30 divided by 5 is equal to 6. And so x must be, let me just double check here, x must be less than 16. Well, this alone is not our final answer because, we're not doing straight algebra. You need to remember that we're working algebra with these geometric figures. And x is part of an expression that describes the size of this angle, and you cannot have a negative measurement. An angle cannot be opened up a negative number of degrees. Now in some maths we talk about angles being negative, but like in trigonometry, we talk about positive rotation, and positive rotation is counterclockwise, and so we talk about positive angles and we also talk about negative angles, but the negative is there for direction, not the size of the angle. So this 5x minus 20, not only does it have to stay less than 60 degrees, and so thus x must be less than 16, but 5x minus 20 also must be greater than 0, because if that angle measure is equal to 0, then you don't have a triangle. And if it's less than 0, that's just not possible. So now we've got to solve a second inequality, which we wouldn't think of from that theorem that we just studied in the previous screen. But we are, again, talking about measurements. So we're going to add 20 to both sides and get 5x is greater than 20. We're going to divide both sides by 5 and get x has to be greater than 4. So we don't just look at the inequalities here and say, oh yeah, x is less than 16. We got to keep an account, again, in the context of we're actually working with real measurements. Measurements must be maintained to keep to be positive, and so our final answer is x has to be less than 16 and greater than 4. Okay, in our last example, very, very similar. We've got two pair of congruent sides, and so we're going to look at the comparison of the included angles. 11 is greater than 9, so that means that, get a piece of white chalk here, that 3x plus 18, this amount of angle here must be greater than 90. That box in the corner, of course, we know means perpendicular, or that that's a 90-degree angle, a right angle. We're going to subtract both sides by 18. And get 3x is greater than 90 minus 10 is 80, and 80 minus 8 is 72. Divide both sides by 3, and we get x is, let's put this over here, x has to be greater than, let's see, there's 2 3s and 7. 3 times 2 is 6, got a remainder of 1, so 12. So 12 divided by 3 is equal to 4. So x must be larger than 24, so that this expression of 3x plus 18 remains greater than 90. However, what is the biggest angle you can have inside of a triangle? The sum of the interior angles of a triangle add up to, you should know this, 180 degrees. So, you know, if the entire sum of all of the interior angles must be equal to 180, then you cannot have a single angle which is equal to 180 or more. Otherwise, you can't make a triangle. So 3x plus 18. Let's see. Let's do this in orange, like this other size check over here. 3x plus 18 must be less than 180 degrees. So again, we're going to subtract both sides by 18 and get 3x is less than 180 minus 10 is 170 minus 8 is 162. And now we're going to divide that by 3 again. And x must be less than, let's see, how many 3's are in 16? That's 5. Now 3 times 5 is 15, but this is 16, so a remainder of 1. And we have, well, not really a remainder for the whole division, but we have 15. So we take the 15 out of the 16, we get 1. Now we got 12, and 12 divided by 3 is equal to 4. And let me just double check one more time with my own notes. Yes. So we've got our final answer is that x must be, let's see here, x has to be greater than 24, and it is less than 54. That is the end of my last example, and that means that's the end of my proof. So, I'm Mr. Troop. Go do your homework.